So today the topic for discussion is empirical processes and covering numbers. And I do want to make a small note. In the last class, there were some questions about finiteness of the action set and the quantization of the action set. So I'm going to qualify those statements in the next class because I don't think I'll be able to get to that point in today's class. So there were early papers that used to do quantization, which is what I was talking about in the previous class. But the newer papers don't do quantization, and I'll tell you when quantization makes sense and when it doesn't make sense. The specific architecture that I had drawn on the board about the neural network, that was from DeepMind's paper, and it turns out that DeepMind was solving the problem which had finite action space to begin with, so they didn't have to do quantization. But then when I talk about more general methods that people have developed, including our group, I'll talk about how to treat general action spaces. But that's going to come on Thursday's class. So in today's class, I want to continue our discussion on what we were discussing in the previous lecture and tell you why even in the general state space setting and general action space setting, why should reinforcement learning converge? Okay. And I won't give you the complete picture because the theory and the practice, there is a huge gap in this particular area. So I'm going to talk about the huge gap, but I'll also tell you why there is a gap, whether or not we should be trying to merge the gap or not, or just let the gap as it is, and the practice will work differently from the theory. So that's the purpose for this class. The today's class is based on two important body of work. One is on non-parametric regression. The text for that is so this one is based on two references. So the first one is Georgi et al. 2002, chapter 9 to 11. The name of the book is A Distribution-Free Theory of Non-Parametric Regression. And the second book is Van der Waart and Wellner, 1996, chapter 1-2. And the name of the book is Weak Convergence of Empirical Processes. And so these two books are extremely complicated. So this one is somewhat more readable than this one. This one is very complicated to read and very terse, whereas Georgi is much more elaborate. It gives you a lot of time to think. Van der Waart is very, I mean, this book is very terse in terms of description. So you have to read it like a math book. Okay. So what were we discussing in the previous? And the third paper is actually my paper. The title of the paper is Probabilistic Contraction Analysis of Iterated Random Operators. And the story of this paper is the paper was written in 2015 and it went through 4 journals, multiple rounds of reviews, finally got accepted and published in 2024. So my paper is certainly inspired by these two references. And we are trying to, what we did in that particular paper was, it was my postdoctoral work, and what we did in that paper was to come up with a general theory of convergence of reinforcement learning algorithms. And so part of my, the entire lecture is largely based on the ideas coming from this paper, which is combination of ideas from Monosh and Sepeshwari paper, which is what I was talking about in the previous class, and these two books. So what we did in the previous lecture, so I have a projection operator. phi f of h, which is, I'm using min. Yeah, let me use just min or argmin of f in f, some norm of f minus h. I know I'm not being clear about the norm because no matter what reference you pick, they have a completely different norm. Munoz and Sepeshwari is using p norm. Georgi is using 2 norm. And van der Waart and Milner is using arbitrary norm. So different papers and books have different norms. So I have a function class f. I want to pick the best fitting function that fits the function h within this function class. Then we have the Bellman operator T of f, which is minimum a in a of s c s a plus alpha. So I'm taking the expectation with respect to W. SAs are constant in this. And then I'm taking minimum with respect to the action in the state dependent action set. I get something which is a function of S. So that's Bellman operator. One thing that I want to note here, you might have a continuous cost, you might have a continuous function here, you might have everything is continuous. But once you apply the minimum operation, you might get discontinuous functions. So T of f could be discontinuous even though you started from a continuous function. And then you might be projecting it back into a set of continuous functions rather than discontinuous functions. So it really depends on what your function approximating class is. You have, as I've mentioned, you have used neural network, you have used k nearest neighbors, you have used transformers and XGBoost. So depending on what the function approximating class is, you might get completely different answers here. But one thing that you know from your experience of running some of those experiments in your assignments is if you pick your function class sufficiently well, you can approximate pretty complicated functions, right? The other thing that I had introduced in the previous class was approximate projection. I denoted it by pi hat of f of h, argmin f in f, and then you have 1 over n summation of I equals 1 to n L of fxi si hsi and then the approximate Bellman operator, empirical Bellman operator, which is T hat of f of s, which is min a in a of s, CSA plus alpha over n, summation So I generate the samples Wi and I pick a state action pair, I evaluate this, I take the empirical mean here, and then I do the minimization operation. Yes?
So we need an I, oh sorry, the I is on W.
Wi, yeah. Not in SNA. SNA are constants for this particular evaluation. Okay. How do you generate these SIs? Generally speaking, In the context of reinforcement learning, you are generating these SIs according to the initial distribution or some base distribution over the state space, which again I'll comment on it in the next class, because the way you generate this has to be very, the way you generate these random states is extremely important, especially when you're solving very high dimensional uh, state space problem. But right now, just assume that you have some way of generating these states and minimizing this function. This pi hat and t hat is using n samples. Okay, so these can use completely different number of samples. So I'm using n because I don't want to carry n1 and n2 throughout the lecture. But please note that you can pick very large number of samples here and very large number of samples here, and you can hopefully get a reasonable solution after running several iterations. The quantity of interest that we want to study today is the following quantity. So if I start with a function f, so what's the original, uh, the value iteration algorithm is vk plus 1 equals to t vk, v naught equals to 0. The empirical fitted value iteration would be fk plus 1 equals to pi hat f composition t hat fk. And f naught would be randomly picked. So f naught can be 0 or randomly picked in f. So this is my empirical fitted value iteration. This is what I can run on a computer. This is what I ideally, if I had a supercomputer, that's what I would want to run. But because I don't have a supercomputer, I can only run this. Okay. So then the question is, how far are these iterations from this particular iteration? If I'm generating the sequence fk, how far is fk from vk at every point of time? So I've personally written many papers on this. When you apply this random operator, so I call this a random operator framework. There's a huge, very long history of it dating back to 1965 when the first few papers came out. So you apply random, so you have a deterministic operator here. You cannot compute the deterministic operator for a variety of reasons, so you apply random operators. And if you keep applying this random operator, what kind of approximation guarantees you can get between what you have computed here versus what you actually want to compute. It's a very fascinating theory, and it has a lot of different applications outside of reinforcement learning as well. Okay. So the quantity of interest that I really want to study is, I know that this particular iteration converges to V star. This one converges to V star. So what I really want to study is pi hat f composition t fk minus V star with respect to some norm. Oh, t hat, sorry, t hat. So pi hat composition t hat of fk minus V star. What's the convergence property of this particular thing? Hopefully, as k goes to infinity or k sufficiently large, this value is small. And if this value is small, it means that I'm close to V star in the specific norm that I've picked. And once again, today my goal is to do it in infinity norm. You pick a paper, they are using completely different norms. You pick a different norm, you have to make strong assumptions. If you pick infinity norm, you don't have to make strong assumptions. You pick some other norms, now you have to make a very strong assumption on F and W for the theory to work. So in my case, I'm going to be looking at infinity norm today. Any question? Yes, please.
Is there a reason they leverage the other ones that the main ones that the ones just easier to have less assumptions?
Extremely good question. So if you're writing an extremely theoretical paper on the convergence properties of these algorithms, you want to focus on the convergence of this stuff. And as I'm going to talk about, Györfi et al. Proves all the results in L2 norm. Van der Waart and Mellner proves result in arbitrary norms. And when you are composing operators with completely different norms, it creates quite a bit of you need to get concentration bounds, and those concentration bounds may not be there in the literature. So the easiest thing to do is to make assumptions on F and W. So what kind of F you have and what kind of distribution W has. If you make those assumptions, hopefully everything will work out. And that's roughly the modus operandi of theory people in RL is, which includes me. And then there is practice people in RL who have to not make any assumption. They just have to show, demonstrate that this algorithm works for playing chess versus playing Go versus solving a complicated problem. So that's why I'm saying there's a huge gap between theory and practice. So in practice, everything works beautifully. In theory, nothing works beautifully, and you have to cobble together different results from different papers and books in order to make it work. Okay. So I know it's not a satisfactory answer, but it's not a satisfactory field to begin with. So, okay, so this is what I want to analyze, and there are multiple ways to analyze this particular. So I'm going to remove Fk. I'm just going to do it for a general F, and then hopefully you can cobble together all the results and get the bound. So I've removed K from here. So this is the thing that I want to study.
Sorry, when you remove the K, what does that mean?
That means that if you can show that this is less than equal to alpha times Fk minus V star plus some error term, like we did in the previous lecture, and hopefully this error is small with high probability, and this alpha is less than 1. And I know that I don't have a norm here, but let me just put an infinity norm. So I'm doing this convergence analysis in infinity norm. Sorry, Fk. Then we can, what I have shown in my paper is that if this is what you have, then eventually what you get is F infinity is close to V star with high probability. So that's the kind of bound you get as K goes to infinity. Okay, so if this is the iteration, so error is small with high probability, then this implies that Fk minus V star is small with high probability as K goes to infinity, or for K sufficiently large. So I'm going to make some of this very concrete as we progress through the lecture, but roughly that's what the English translation of all the math we are going to do in today's lecture is going to be. This part is actually coming from Munoz and Sepeshwari did the initial analysis, and then my paper did the rest of the analysis to do it for a more general setting. Does that answer your question? Yeah.
Almost, but so if you remove the K on F, then are we just thinking of F as arbitrary?
F is some point in the function space, this capital F.
But I mean, it kind of removes it from the iteration. If we take away K, then it's sort of like saying we're not considering the
That's right. So we are doing it for general f. Now, as you are picking f1, as you are going through the function space f0, f1, f2, f3, you basically get the same result for all f's. Yeah. Any other question? Okay. So is the roadmap clear for today's lecture? Okay. So the way to generally study this kind of, so you have two operators minus a function, and you're picking some norm and you're trying to find the difference between the two. The general recipe is as follows. So this is recipe number 1. Recipe number 2 is that's the second recipe. Any questions so far? No? You can of course pick whatever norm you want, and then those norms will have to be propagated throughout the entire proof. But I'm going to do it for infinity because it's much easier and simpler to do it for the infinity norm. Any questions so far? Okay. So when is this? So generally speaking, this alpha times this norm comes because of this final term here. Okay. So so this one comes from here. This error comes from these two errors. So how well can t hat approximate t? So look at the t hat and t operators. How well can this empirical averaging approximate the expected value? You have seen Hovding inequality, and we are going to be using that today. Okay, so that's this one. What about this one? How well can pi hat f approximate the function t hat of f? Okay, so t hat of f is, it could be a continuous function, it could be a discontinuous function, it could be a Lipschitz function. I am picking this particular function, so this is replaced with t hat of f. So if I replace it with this t hat of f function, how well can my function class approximate the function that is coming out of this particular operator? So that's this one. So ideally, my function class f is very, very rich, like very deep neural networks, or very or very, very well handcrafted features so that your function space can take in any complicated function that might come out of this t hat of f operator. So then in that case, this particular norm is going to be small with high probability. So this norm will be small with high probability if I pick this n sufficiently large and my function class f is sufficiently broad. Then this norm is going to be small with high probability. This norm is going to be small with high probability. So whatever error you are seeing here, it comes from your function approximation and your empirical computation. And the same thing happens here as well, except that the kind of inequalities you get would be quite different. So I'm just going to focus on this particular thing. And what I'm going to do in the rest of the lecture is I'm going to show you that the convergence of this, sorry, the error process that this one generates and the error process that this generates, it actually comes from the same mathematical principle. And that mathematical principle is known as empirical process. Okay, so we'll talk about empirical process and how it connects to Hopding inequality. Okay, any questions so far? Okay. Now, in the future, when you are running reinforcement learning algorithm and it fails, your reinforcement learning is failing, it could be because this error is too high, it could be because this error is too high, or it could be because your f is very small and you need to enlarge f. So if you go to Google or DeepMind, their entire goal in life is to increase the number of samples n here, increase the number of samples n here, and use extremely complicated function approximating classes running on hundreds or thousands of GPUs. And that's roughly how they are able to solve all of this complicated reinforcement learning problems. Okay.
By increasing f, you means increase the number of functions?
Increase the complexity of the function class. So instead of using, so for instance, if you wanted to train a neural network on your computer, you might use 5 layers, 10 layers. But if you go to Google, they are using like thousands of layers. 1.8 trillion parameters. What does 1.8 trillion parameter means? It means that your function class f is extremely complicated, like it's way too complicated. It's so complicated that you can't put it in a single machine. You have to use distributed servers to be able to do that computation. Okay, any other question? Awesome. So I'll keep that board and I'm going to erase this side. Okay, so I have an argument here, I have an argument here, I have an objective function here, I have an objective function here. Generally speaking, if this is the L2 norm, you pick this loss function as an L2 loss function. So you take FSI minus HSI square, that's your loss function. If you look at the application literature, they might pick some other loss function here. So not just L2 loss, they could use regularization, they could use some other things. We're not doing anything with regularization right now. And we are just going to assume that this loss function is picked in a way that it's compatible with the norm that you have picked here. So if it is infinity norm, you want to pick an infinity loss function here. If it is L2 norm, you will pick the L2 difference between FSI and HSI. And Georgi is using L2 norm in these computation. So, so that's just something you want to keep in mind. Okay. So what's the idea from Georgi et al? There are multiple ideas there, but the main one that I'm going to talk about today is the fact that I want this particular empirical number and this norm to be very close to each other with high probability. So the question there is, under what n should I pick for 1 over n summation I equals 1 to n L F S I H S I to be close to F minus H for all F in F. This is question number 1. Question number 2, what n should I pick for t hat f minus t of f infinity, or I'm using approximate equality. So let me use approximate equality. Yes, please.
I think since the loss function, we should still have some requirements on the loss function, like also.
Yeah, so you definitely want the loss function to be a metric, but it doesn't have to be a metric. For instance, it could be like square of, so f of Si minus h of Si square 1 over n summation I equals 1 to n. This is not a metric. This is a metric. Okay, so there is a requirement that this loss function should be, the loss should be 0 when these 2 points coincide, and it should be increasing away from 0. That's a requirement. But the reason why I'm writing general loss is sometimes people use cross entropy loss, and they are not written in this particular form. In fact, they are not even a metric. So I'm trying to be general here when I'm writing it, but when I get to the actual proof, it'll be very specific. So I'm actually going to be using this loss. And I'm going to assume that Si is distributed according to some distribution. Let me use C, and then F minus H will be square root of integral of Fs minus Hs square C ds. And this is over the entire state space S. That's the norm I'll be picking. So SIs are generated according to the distribution C in an IID fashion, and this is the loss that we want. And then I'm going to make sure that this particular thing is approximately equal to the F minus H square, because I have to then take a square, because I'm not doing square root here, so I cannot do square root here. It's just that solving this problem is comparatively easier than solving it with a square root. So that's why people remove the square root and solve the problem. Yeah.
Is the sampling IID?
In today's lecture, the sampling is IID. In practice, sampling is never IID. That's another difference between what happens in practice versus what happens in theory. Okay? Yes.
Sorry, so
Yes, please.
we have a square on the sum, but then the other one is not square?
Right, so that's what I was saying, that if I'm using this particular loss function without the square root, I have to make the square here.
Right.
And that's what I'll be proving in the
So
class.
that's what we're doing.
Yeah, that's what we'll be doing in the class. Okay, so these are the 2 questions, and I'm going to say that these 2 questions, in the next 5 minutes or 10 minutes, I'm going to show that these 2 questions essentially boils down to proving the following result, or asking the following question. So I have D which is a set of D from S to R. It's a subset of the set of all measurable functions from S to R. And I want to know if probability of supremum over D in D 1 over n summation D Si, I goes from 1 to n, minus expected value of D greater than epsilon is less than delta. And delta, of course, depends on epsilon, D, and n. So both question 1 and question 2 gets mapped to this particular question. So I have a set of functions, and I want the empirical expectation of the function to be close to that expected value of the function with absolute value here for all the functions in the function class. Greater than epsilon, it should be bounded from above by something which is small. Okay, so this is the kind of bound we will get. Exactly this bound is studied under the umbrella of empirical processes. Okay, that's what this theory is about. And you might have heard of terms like VC dimension, Rademacher complexity, covering number. You may have, you may not have, but all of that is properties of the function class D, so that this particular statement holds. Okay, so for general D, this statement will not hold, but if you can narrow down the set of D, then this statement will hold. And what I'm going to show is this problem and this problem boils down to this particular theory, and then we'll talk about this theory. Hopefully I'll have enough time to cover that. Okay, so now I'm going to pick the specific loss function, and I'm being a bit hand wavy here. So remember, I was telling you about infinity loss, like I want to understand infinity loss and so on. The problem with infinity loss in the projection operation is nobody has studied it very well. So the theory is extremely scant on the infinity loss. For L2 loss, the theory is very well known. Okay, so for L2 loss, I'm picking this stuff from chapter 9 to 11. For infinity loss, I myself don't have a good reference to check where do you study the infinity loss, where do you study this projection operator with infinity loss. So I'm going to do the hand wavy thing and say that, okay, I'm going to do this. Square, and this is integral of fs minus hs square cds for all f in f. So this is what I'm going to study now. Okay, so let's so while I'm erasing this side of the board, I want you to think about this statement and this statement, and I want you to figure out what this function class D should look like. What exactly is this function class D? So that's your homework for the next 2 minutes. Anybody who completed the homework? No? So this is what I want to show that this is close to this for all f in f, and I want to figure out what's my function class D. What do you think D is? For question 1. So this function class D depends on my function h that I want to approximate, and it's given by this particular expression. What about question 2? What is D of h? Sorry, not h. There is no h here. This is D of, okay, not S but W. D of W equals to F, no. There exists an F in F. There exists SA in graph of A, such that D of W equals to F, capital F SA W. There exists an F such that. Okay. So remember, I want to show that this term is almost equal to the expected value. So the empirical squared loss is the same, is close to the expected value with high probability for all f in f. So the way I construct this function class D is by picking the square loss at every s, and now my function f is so there exists an f such that this particular statement holds. So the set of D will be as large as the set of f, because I'm taking the square loss for every f in f, and that's creating the function class D. Yeah, you have a question?
What does that mean in question one? Okay, arbitrarily for all f that we use to approximate their so like.
No, so I'm just picking one of those f. Okay, so what does it mean? Let me write it in other way, because that might make things easier to understand. Does this make sense? Okay, so I can do the same thing here as well. I can take the union over all f and union over all SA, and that will give me a specific set of functions. Any other question? Yes, please.
What's the meaning of the W exactly?
W is the noise.
Yeah, but as a like a space.
Yeah, as a space now.
So
This is D that takes as input a noise variable W and outputs a real number.
could we just say that W is real? D maps.
W could be in Rm, so you don't necessarily need to have a noise which is just a real line. You could have a n-dimensional noise. So in case of, let's consider the case of Uber, and the noise variable is how many passengers are requesting Uber in a city. So the city could be like a grid, and how many passengers are requesting Uber from each grid. Like you can make 2 blocks cross 2 blocks grid, and then then the W will be the number of grids, like n raised to the number of grids. So W could be more general than just real line. Yeah.
So the first question to the W, TW is a small W. This is the
This is the space of W, space of noise W. So like I was mentioning, this W could be n raised to m, for instance. It could be very high dimensional space. You know, we are in the general setting, so I can't put a structure on W. Any other question? Okay. So I think for this part, you can easily map based on the DH. You can easily map this problem with this problem. For this one, it's a bit complicated. So let me show you how I got this D class here. So T hat of F minus T of F infinity You may choose not to write it because it's going to be a fairly long expression, but it's up to you. Minus Do all of us agree that this is what this is? And what did you prove in assignment 2? Question number 2. That if you have a minimum of a function and minimum of another function, and you take the infinity norm, that's less than equal to sup SA in graph of A, this function minus this function. So that's 1 over or alpha over n summation I equals 1 to n FFSA WI minus alpha expected value of. So that's how I picked this particular thing, because I'm using F composition F evaluated at SA. So that's why I picked F composition F evaluated at SA here. And now I only have a function of W because I'm only doing empirical averaging with respect to W here. Any questions so far? So I have a projection operation. I cannot do projection operation. I'll take the empirical average, and I'm empirical average of the loss, and then I'm going to minimize that loss, and hopefully this loss is approximately equal to the true loss that I'm interested in. And the second part was I cannot compute the expectation of this whole thing. So I'm going to take the empirical average because I have a simulator, but I don't have the actual noise distribution or something. So I'm going to do the simulation. So how close is T hat with respect to T? What we did was, if you want to study how close this is with respect to this and how close this is with respect to this, and the error is small at every point of time during your value iteration algorithm, then these two problem statements actually boils down to this particular problem statement. So if you have a function class D, you take the empirical average and you take the expectation supremum over all of these function class, this error should not be or should be greater than epsilon with very small probability. Okay. So this is the problem. And now the question is, how do I solve this problem? So I was able to figure out that these two problems get mapped to this problem. Now I only have to study this problem. And now the question is, how do I make sense of this particular equation? So let's look at a very simple problem, okay? And then I'll get to that particular problem in a bit. So the simple problem is, it's called the union bound. I'm assuming that you have not seen union bound before, so I'm going to derive the union bound, and then I'll get to that particular problem. Okay, union bound. So I have two random variables, x1 and x2, that maps omega to R. So these are all mapping from some space of uncertainty to R. So real number valued random variable. I know the value of, probability of x1 greater than equal to epsilon and probability of x2 greater than equal to epsilon. And now somebody told me that I need to figure out what's the probability that max of x1 comma x2 is greater than equal to epsilon. Somebody asked me this question. This is what I know. This is what somebody asked me. How do I solve this problem? Okay, so whenever we are faced with problems of this type, the easiest way, the simplest way that I know is to transform it to the very basics. So I have a set A1, which is omega in omega, such that x1 of omega is greater than equal to epsilon. I have a set A2, which is omega in omega, such that x2 of omega is greater than equal to epsilon. And I have a set A3, omega in omega, max of x1 omega, x2 omega greater than equal to epsilon. I am personally very comfortable with sets, so I put everything in the set notation. And the question really is, what's the probability of A3? What is the probability of A3? I'm going to claim that A3 is a subset of A1 union A2. Does this make sense? I'm going to claim that A3 is a subset of A1 union A2. So why should that be the case? So I pick an omega in A3. So I know that the max of the two random variable is greater than epsilon, greater than equal to epsilon. So at least one of them must be greater than equal to epsilon, at least one. So either this is true or this is true. Either omega lies in this or omega lies in this. That implies that A3 is a subset of A1 union A2. Because I know that if omega is in A3, then either omega is in A1 or omega is in A2. It could be in both, so there could be overlap, but it must be in one of these two sets. Consequently, probability of A3 is less than equal to probability of A1 plus probability of A2. Because probability of union of two sets is less than equal to probability of sum of the probabilities over those sets itself. Okay, this comes from the basic probability theory axioms. So this comes from the basic probability theory. I hope all of you are aware of this. If I knew that A1 and A2 are disjoint, then there will be an equality. But because I don't know that they are disjoint, I have less than equal to sign here. Okay. So what this implies is that probability of max of x1, x2 greater than equal to epsilon is less than equal to probability of x1 greater than epsilon plus probability of x2 greater than epsilon. This is known as the union bound. I mean, this is a special version of the union bound, and the general version would be you have max over n random variables and you have sum over n random variables on this side. Any questions so far? Okay. So I'm going to write it here. That probability of max over I xi greater than equal to epsilon is less than equal to summation over I probability of xi greater than equal to epsilon. You can have finite number of indices or you could have infinite number of indices. So I'm leaving the index set open because you could have any number of indices, finite or countable, and that statement would still hold. As long as the number of index is countable, this statement would hold. Okay, wonderful. So I have something like that going on here. So this is my xi. This whole thing, absolute value is my xi. I'm taking supremum over a set. So it's an uncountable set now. It's no longer a countable set. So now I have a problem. I have a problem that I know this union bound. It holds for all the countable index set. Certainly it holds for finite index set. For countable, the problem is that each of these probability could add up to infinity. So that becomes a problem. But with finite, hopefully it will be below 1. And then it would be a reasonable bound. Now the problem is I have this uncountable set So I can't apply the union bound. So somehow I have to do something, I have to do some magic to replace this supremum over D to something that is a countable set, or at least a finite set. Like ideally it should be a finite set, not a countable set. So let me ask you one question. Suppose there was no supremum here. Is this easy to do? If I don't have the supremum here, I'm erasing the supremum here. Would this be, what would this inequality be called? That's Hoeffding inequality, right? Hoeffding. Now there are of course tighter versions of Hoeffding inequality and all that stuff. I'm not going to get into that, but Hoeffding inequality will, without supremum, Hoeffding inequality will give you this particular delta. And in Hoeffding inequality, the delta is a function of epsilon and n. Okay, there is no d there, epsilon and n, because there is no d. So I can apply Hoeffding inequality. So what I mean to say is computing this is easy. Probability of xi greater than equal to epsilon. So that's easy. The real challenge is the fact that I have an uncountable set here. So I can't apply the union bound. So I need to replace this with a finite number of sets. And that's where the idea of covering number comes in. So I'm going to define covering number now. Any questions so far? Because I think now we are going into more complicated stuff. Okay. A set C is called an epsilon cover of D if for every D in D there exists dj in C such that D minus dj is less than epsilon. So once again, this covering number can be defined for any norm. We are interested in infinity norm. We are not interested in other norms, but you can have any norm here for the definition. So the size of smallest epsilon cover of D is called the covering number. And it's denoted by, I'm going to denote it by n epsilon D infinity.
So that it looks like the epsilon match in the compact set.
There is a connection, but
I think there are the first two lines are just, I think, equivalent.
right. So the covering number of compact sets is always finite.
Oh, yeah.
Because you are picking a norm, you're picking epsilon ball around DJ, open balls, If this set is compact, then you know that there is a finite subcover. So that's true. So the covering number of a compact set is always finite, but every set which has a finite covering number doesn't necessarily need to be compact. Okay, so the other way doesn't work, but the forward way works.
This is a further assumption.
Yes, we will make this further assumption on the set D that the covering number is finite. So typically speaking, if you pick an arbitrary set, the covering number is going to be infinite. So you need infinite number of functions to be able to cover the entire space. Okay, but if D is Lipschitz continuous and bounded, then it has a finite covering number over a compact set. So if the state space is compact, this D is the set of Lipschitz function that is bounded by a uniform bound, and the Lipschitz coefficient is also bounded by some uniform number. Then it has a finite covering number. So then this N is finite. So we are interested in the set of D which has a finite covering number. We are not interested in set of D which has infinite covering number. Needless to say that in practice, nobody checks for covering number, but in theory, covering number is important to get the bound. Okay. Any question? Okay. Wonderful. So I started with this. I started with this particular thing. So I know that for each xi, I can figure out this inequality using Hoeffding inequality. Now I have supremum over all D. I'm going to replace this supremum with the set C, which has the smallest covering number. So the number of points in C is the minimum. It's exactly equal to this number of points. The book that I talked about, weak convergence of empirical processes, that has a whole bunch of sets for which the covering number is finite. So you will see the set and you will see the proof that the covering number is finite. This theory is actually extremely well developed for machine learning problems. So people talk about covering number of neural networks, covering number of transformers and things like that. So this theory is extremely well developed for machine learning situations, and some of that discussion you will find in the paper in the book that I talked about, the second book that I talked about. And it's also there in the first book. So Györfi also talks about covering number, and the other book, Van der Waart and Wellner, that also talks about covering number. Van der Waart and Wellner actually has derivations of all the covering numbers. So that's, if you're interested, you can look into it. Okay. So now here is the result. So suppose D infinity is less than equal to B for all D in D. This is a theorem. Then the probability of sup D in D 1 over n summation I equals 1 to n dsi minus expected value of ds greater than epsilon is less than equal to 2n epsilon over 3 d infinity minus so my D's are all bounded by a number capital B. then the probability that this, for all d, this thing is greater than epsilon is very small. I just did some calculation because I wanted to get a sense of how many n do I need in order to get a small probability of error. So let me write that down. I'm going to share the proof. The proof is just 5 lines proof, so it's not going to be a complicated proof for this theorem. Because I don't have time, I won't go over the proof in the class. It's very simple and straightforward, but I've talked about all the important things I wanted to talk about. So if b is equal to 2, if epsilon equals to 0.01, if delta equals to 0.01, and the covering number n ten raised to 10, then n equals to 20 million. So if you want to have a reliable estimate of, for all functions d, you want to have a reliable estimate of the expected value using the empirical mean, you need to use 20 million samples. This n has to be 20 million. In practice, n is 5 or 10. Okay, and it still works. So, I'm not making a joke here, it works. Okay, with n equals to 5, it works. In theory, it should be 20 million. In practice, for 5 or even for 1, people have made it work. Yes. This is the worst case bound. This is supremum over all d in the set D. The space of all Lipschitz continuous functions that are bounded and has a Lipschitz coefficient less than equal to something. When you're doing value iteration, you're not going all over the function space. You're visiting some specific functions during the process. Each of those functions that you are visiting is a function of the noises that you have picked in the past and the minimization that you have done. You might have done approximate minimization and whatnot. So when you are proving these bounds, you are picking the worst case. In reality, you're not going through the worst case set of functions. You are probably going through all the benign functions in the space to the optimal solution, which is close to V star. Okay, so that's roughly what the reason is. And that's the difference between theory and practice. So in theory, I need 20 million noise samples at every point of time, and I need to evaluate this t hat of f at 20 million state points in order to be able to make sure that pi hat composition t hat is close to t hat, close to whatever, close to the actual pi composition t. But in practice, we only take 5 samples and a few more samples here and there, but we run a large number of iterations. So our k is very large. K could be 100,000, 1 million or something, but the samples that I'm picking at every time step is very small, and it still seems to work in practice. Okay, and so there are a few things that we covered, and I want to sort of convey the ultimate message. The few things that we covered was inherent Bellman operator, which is a function of the Bellman operator and the function of the function classes that you have picked to approximate the Bellman operator, to do the function projection. So if you want to solve a reinforcement learning problem in a general state space setting, you want the inherent Bellman error of the function approximating class to be less, which again depends on the function class and the Bellman operator. And you are doing an assignment right now where the inherent Bellman error becomes 0. It is infinity to start with, and then it becomes 0 by just adding additional terms in the function approximating class. And so you start with the question number 5b, you will see that the error is huge. Question number 5c, you will see that the error is 0 at every point of time. Okay, so you have to pick a function approximating class with inherent Bellman error as small as possible. You have to pick the number of samples n for the function projection sufficiently high, and I'm using sufficiently high in theory 20 million, in practice 5, and you have to evaluate this t hat of f at 20 million states in theory, and maybe 20, 30, 50 states or 100 states or 1000 states in practice. Okay. So this is, so I did this for empirical value iteration. You can do exactly the same thing for empirical Q iteration. So Q iteration was also something that I had introduced the operators pi and t for Q functions. You can do the same thing. And so what I'm going to do in the next class is I'll talk about how people have used general state space reinforcement learning ideas in real world. I'm saying real world, but some of it could be DeepMind paper. So DeepMind is working more on playing chess and Go back in 2015-16. So I'll talk about what people have done for reinforcement learning, and so sort of practical reinforcement learning for very high dimensional state spaces. So in our group, we have solved reinforcement learning where the state space was 1,000,000 dimensional and the action space was 1,000 dimensional. So I'll talk about that as well, as to what are the different considerations you need to have when you're solving problems of such high dimensional state and action spaces. We'll talk about that. And next class on Tuesday, I'm going to talk about generative AI. So specifically reinforcement learning with human feedback. That's an extremely hand-wavy topic because there's no theory there. It's all practice, practice, practice. So there's no, so I think this is the last theory class in this semester, after which the 2 classes are going to be practical. So no complicated probability and stuff. I just wanted to show you the elements that you need to worry about in the general state setting. So the 2 classes are going to be practice, and then December 2nd, 4th and 9th, all of you will be presenting in the class. So hopefully all of you will present on time, so 10 minutes each. And so we'll learn about all the 25 different applications that people in this class are studying, where reinforcement learning is utilized, and hopefully that'll allow you to collaborate or find collaborators or just chit chat with other people in the class about whatever problems they are interested in and what you are interested in. Okay, so that's the, yeah, go ahead, please.
Would that be like an 8-minute presentation with some time for questions, or is that a 10-minute presentation?
I am not going to allow for questions because that might exceed the time limit. So whatever questions you have after the class, we can just meet outside and we can chit chat on the corridor. Okay.
So
Yeah.
For the presentation, we may need a PPT, and so where.
So I'll be downloading the PPTs. So the sign up sheet has already been sent out. So everybody has signed up. So on day 1, there'll be like 7 or 8 presentations. So I'll put all those 7 presentations on the computer.
That's my question. Where is the projector?
That's the projector.
Oh, I see.
And this is the,
Oh, I see.
this is, yeah, the screen. Yeah.
And another question about
Yes.
so the unit value.
Yes.
So I think it's permissive. Okay, permissive. But it is still what we get
Uh-huh.
for estimation like this P maximum or super.
That's right. Yes.
Well, my question: we only get unit value. Is there a better way for the estimation?
So far, no, but you can work on it. There is no other better way than, okay, you can tighten these bounds slightly based on the stronger version of Hovding inequality if you knew a lot more than the fact that d infinity is less than v. So for instance, if you knew the covariance of expected value of d of s, and you know that for all d in d, the covariance is small, you can then tighten this bound quite significantly, but the covering number will still be here. And the covering number is exponential in the dimension d. So if my state space is Rd, the covering number would be generally d over epsilon raised to d or something like that. So the more dimensions you have, the higher the covering number is going to be. And so this one is going to be very large. This is the only part that you can tighten based on more assumptions on this covariance of d and so on and so forth. But whether you can tighten this particular bound or not is still sort of an open problem. Yeah, but I'm not going to say that this is the only way to do it. There are other ways also that people have studied, but almost in all cases, the number that you get here is very large. Okay, that will not be small. Yes.
So what are the requirements on the distribution of S?
For this particular thing to hold, there is no requirement on distribution of S. S could be arbitrarily distributed. And for covering numbers to be finite, generally speaking, S needs to be a compact set. For covering number to be finite.
And the SI IID believe, right?
SIs are IID. Again, another thing where theory and practice differs. In practice, SIs are all correlated because it's coming from a Markov chain. So then there is some way to subsample from the Markov chain in order to sort of make sure that SIs are roughly IID, but there's no proof. So next class we will talk no proofs and only how people implement. And I don't know how it will make sense, but I'm sure you will be able to figure out whether you can use it in your setting or not. Okay. Any other question? No? Yeah, perfect. Thank you so much, and I'll see you on Thursday.